Hello, everybody. I hope you are doing well. Sorry, I'm very tired. I wanted to go over energy and chemistry tonight. I am going to do a quick thing on properties, really quick on properties and changes. I know you watched some videos on those, but I just want to do my own on it. Also, I was at a family Christmas pajama party today, hence my O Chemistry shirt. Anyways, there was a wedding and everybody was in town, so we were doing Thanksgiving, Christmas stuff all in one day. Starting off just with physical and chemical properties, I know you guys already did this, so I'm just going to cover this stuff really quick. A physical property is something is a property that a substance displays without changing its composition. So, right, this bottle of whiteout marker is white. It is plastic, which means it's fairly hard. It's not soft, right? But it's not that strong, so it is a bit pliable, right? I could probably break this bottle if I really, really needed to, and you gave me, a few minutes to just really go at it. Right? This medicine canister is metal. It's shiny. It conducts electricity because it's metal. Right? It, again, is hard. Right, so those are physical properties. I can see those, I can observe those without changing something. But chemical properties are things that can only be observed, right, when the chemical is changing. Like flammability. If I light this box of tissues on fire, it's going to be a different chemical. Right, it's going to burn up. It's not going to be paper anymore. Whereas if I smash this controller and destroy it with a hammer, right, that's not changing the chemicals. It's all still the same stuff. It's just physically destroyed. So things like rusting, right, that's a different substance. It changes into a different substance. Right, so go through, right? So again, odor. That's a physical property. Well, flammability is a chemical property. You can smell gasoline, right? It's a pretty distinctive smell without changing the property. But you can't burn it without changing the property. Now, some people are wondering, because we do have sensors in our nose, right? The way odors work is we get some of the chemical, it comes in, it actually chemically binds with our nose. And that might be a chemical reaction, but it's not a change in composition, because afterwards our nose then lets go of that gasoline, right? And we don't keep it. So we might have those types of interactions where it grabs something and it sends the signals to our brain, but right, it doesn't change the chemical. So an important note here is a change of phase, that is boiling or evaporating or freezing, condensating. Any type of phase change is a physical change. That's because the chemical isn't changing its composition. It's just changing how far apart or close the things are. So if you remember when we talked about those solids, liquids, gases, right? A solid is when it's in this rigid formation. Liquid is when it's free moving. So if you put enough energy into that solid that it starts moving freely, the substance isn't changing. It's just gone from being rigid to freely moving. So those are not chemical changes. those are physical changes. The composition is staying the same. Right, so a physical property, for example, would be the boiling point, the point at which something boils, where boiling is a physical change. Right, so boiling point is the property. The process of boiling is so boiling point, physical property, process of boiling, physical change. Right, so state changes are always physical changes. Matter changes its appearance, but not composition in a physical change. Right, if you cut a piece of meat, right, it might change its appearance, it's become smaller. Each piece has become smaller, but its composition is the same. Melting ice, it looks different. Composition is the same. Chemical changes are when matter does change. One way you can tell something is in a chemical change, you can't always tell just from looking. But one way you can tell is to look at the physical properties. Usually, a chemical change will change the physical properties because the new chemical will have different properties. The density changes, the color changes, the smell changes, right? Taste changes, although we never taste things, but you can, taste is mostly smell anyways. Right, the texture changes. These are, right, often signs of a chemical change, because if the physical properties change, the chemical itself must have changed. You can still get a change of properties, or at least a seeming change of properties from mixing stuff. You mix lemonade powder into water, and all of a sudden, right, it tastes lemony. Well, yes, the properties of water have changed, well, but not really. The properties of water are the same. The properties of the lemon powder are the same. They're just kind of averaging out, right? They're combining and mixing together, not making whole new properties. All the properties are happening at the same time, giving you the watered down lemony taste. So keep an eye on that, right? Make sure something isn't just a mixture. For example, right, food color. We might think of food coloring as, for example, hearing that, go, oh, all right, color change, chemical change. Well, no, that's just mixing, and it's averaging, like, water is colorless. It doesn't actually have a color, right? So if you put in a food dye, which does have a color, it evens out. Whereas if you take, like, white frosting and you put in red food dye, it might end up as pink, averaging out. Or if you put in enough, you might end up as red. Chemical properties, right, and chemical changes appear together. If something is oxidizable, that means it is susceptible to rusting, to combining with oxygen. Well, at least iron is susceptible to rusting. In silver, we call it tarnishing, right? Copper, we usually just call it oxidation. Right? Statue of Liberty turns green, but we also see it in our pennies, right? When they get that dull brownish look. There are different ways chemicals will react with oxygen, so it might lead to different colors. We have a lot of different examples of this. When we burn magnesium in the lab and it turned white, right? That is oxidation. So the chemical property of that, right, is that magnesium is oxidizable in the presence of heat. Well, right, the oxidation of it, the reaction where the heat caused it to give off a bunch of light and rapidly react with oxygen, was the chemical change. So iron, right, when iron rusts, it physically turns into a different chemical. The iron combines with oxygen. And finally, right, matter undergoes a chemical change during a chemical reaction. So that's all a reaction is. A reaction is the specific formula and the process of a certain chemical change. Right? We look at an example of a reaction. We say, look, we combine these two things. There was some sort of, reaction. Right? Reaction literally coming from the idea of like, oh, you punch somebody in the face, they're going to react to that, right? You combine these two chemicals, they reacted. Sometimes you combine two chemicals, they don't react. So here's just a summary. Pause and read this if you feel like you need to understand. But beyond that, I'm just going to keep going. Real quick though, I just want to give you examples, a few more examples of physical changes. You press down the button on a lighter. This changes the pressure and allows butane to vaporize. Right? You have the liquid. The liquid comes out as a gas due to pressure changes. That's a physical change. However, you spark it and you burn it, well, that's a chemical change. Right, now they're reacting with oxygen and you sparked a flame which is needed to get the reaction going. One quick thing I want to talk about, this is pretty unrelated, it's just going to be kind of an aside. It's still fair game for a test or quiz, so jot it down, but it's just slightly related to these properties we talked about. We can use these physical changes to separate chemicals. Separating chemicals is an entire field, right? I could go on for hours of different methods to separate. I could teach a whole class on different methods of separating chemicals. I'm going to talk about just really simple ones though. Physical changes. Right, physical changes using to separate chemicals. One of them is just like condensation or boiling, right? Change of state. So, for example, here's one, but I'll actually kind of give two here. This is an example of distillation. This is how we make alcohol. You take a mixture of liquids, might be alcohol and water, and we want the alcohol to be stronger, so we boil it. Right, alcohol boils at a lower boiling point. So the alcohol goes up and then it comes down here and we just have some cold stuff in here, so when it touches the cold stuff it turns back to a liquid, gets down here. We leave the water here, put the alcohol in there, we're good. Right, that is distillation. It's a physical change causing them to separate because they have different boiling points. They have different physical properties, so one of them is going to boil faster. Another would just be evaporation. If you have a solid dissolved in a liquid and you want to separate them, just evaporate the liquid. The liquid goes into the air. You can collect it if you want. If you only want the solid, just evaporate it, who cares? If you want the solid and the liquid just to be separate, have something like this. You could boil all the liquid, get the liquid down here, leave the solid in here. All right, or just do it in a less complicated setup. So, that one is filtration. If you have a solid and liquid combined, they're not dissolved. You need to get rid of them. Put a filter here, like a coffee filter, right? Something similar to that. We use chemical filters, but really it's the same idea as a coffee filter, just like finer. You pour the liquid through, the liquid drops through, the solid doesn't. Now, for a coffee filter, we already have the coffee bean separate. We pour the water through, and it kind of dissolves some of that coffee and it takes some of it into the liquid as it goes through. Kind of, that's a really big oversimplification. But here it would be, you have the solid and liquid, they're not dissolved, you're just trying to separate it. So you pour it through, liquid goes through, doesn't. Other physical ones, like you guys know, I don't really need to go over, right? A 3-year-old knows, like, you could use like a sieve to like get the small grains to fall through, keep the big grains in, right? You could physically separate solids. You can go through and pick them all apart, right? But these are kind of more advanced techniques that would actually be used in a lab. I won't cover anything more than this. There are extremely advanced techniques not extremely, but like fairly advanced college level techniques for separations, tons of them, and then beyond college level, there's even more, but we won't worry about that. All right, and the last thing I'm going to cover before we get to energy. This is something I promise will be on a test and will be on your midterm. This is, once again, law of conservation of mass. We've already talked about this. This was Antoine Lavoisier. I apologize for my very stuffed nose. I was at a place that had a dog today, and I'm very allergic to dogs. At least I hope that's it. I hope I don't have a cold. So, matter can't be created or destroyed in any kind of chemical reaction, right? Except in nuclear reaction, we're not doing nuclear reactions. So, in a chemical reaction, matter is not created and not destroyed. The total amount of matter remains constant, both in a physical or a chemical change. The chemical change bit is important. Let's look at this idea here. We talked about burning the fuel in a lighter before, butane and oxygen. Carbon dioxide, right, makes carbon dioxide and water, makes CO2 and water. Okay, the total amount of butane and oxygen you burn is going to equal the amount of carbon dioxide and water you burn, which means if I give you all of the reactants on the left and all but one of the products on the right, or all of the products on the right and all but one of the products or reactants on the left, you can solve for whatever's missing. Or I could give you information. I could say like, oh, right, A plus B react and they make C and D. How much C and D do they make? Right? Or I could say like, oh, A plus B completely react, all of it's gone, and they make chemical C. You had X grams of A and B grams, or Y grams of B. How many grams of C did you make? Well, it's X plus Y. Right? You just take the amount of A and B you had, add them together. So if this was one chemical and this was your unknown, you could just say, oh, well, 58 plus 208 is 266. And so this has to be 266. Right? Whatever the case is, if you don't know one of these, you know the rest because you can just put a big old equal sign right there. I'll cover that when we get back. Like, we'll do a little bit of practice on that. It's really straightforward. I don't think we'll even do like a homework on it. Maybe just one or two quick problems in class. It'll probably be on a test, probably be on the midterm, but this is like usually super easy. As long as you know how to do it, it's just addition. So not really anything to worry about as long as you remember the law of conservation of mass and remember what to do. All right. Now to get to the meat potatoes, although it'll really only be half of this, but this is the important stuff. Energy. Energy is big. Our universe is made up of energy and matter. So energy is kind of one of the big components. Energy is really the only thing that isn't a chemical, but energy is still intrinsically important to chemistry. It's always, right, an important topic. In fact, right, I am a spectroscopist in which all of my work is related to, right, energy. All of my research, pretty much, has to do with energy. So, energy is the capacity to do work. What do I mean by work? Well, work is force acting over a distance. So, right, if I get up, I have this chair. Right, force would be the pushing that I was doing on the chair. Acting over a distance would be work. So, pushing this is really just force, right? Well, okay, the act of pushing, even if you're not pushing it a lot, you're probably moving it a tiny amount that you may not even define. So the act of pushing, the amount of force in pushing, that's the force. Work, right? Up like that. Energy is the capacity to do work. So I have energy stored in my body. When I start doing work, that is a type of energy, right? I am using that to move this chair up. Once I move this chair up, this chair has potential energy. The second I drop it, right, it crashes down because it has its own energy, right? So if I rigged up some sort of system, but by crashing that down, right, if I push it down onto something, it could launch something else up in the air, right? Because it also has the capacity to do work as potential energy. Behavior of matter, which really is the crux of what chemistry is, right? Chemistry is trying to understand how matter behaves, is driven by energy. In fact, energy is maybe one of the most important things in chemistry. Energy and electrons explain basically all of chemistry. Just like matter, energy is conserved. It's the same law. Energy isn't created or destroyed. So, the total amount of energy in the world is constant. You can't get rid of energy, right? You can only change it from one form to another. There's a lot of different forms of energy, right? Heat, right? There is kinetic energy, like physical motion, right? There's potential energy. When I had that chair stored up in the air that had potential energy, the second I let go, it turned to kinetic energy. You can transfer energy from one object to another. If I hit my hand, right, I'm transferring kinetic energy. I can heat something up. Energy can be in the form of electricity, right? There's a lot of different forms of energy. Some of the ones we don't always think about in a moment, sound, right? So for example, if I drop a ball and it bounces and it comes back up and it doesn't go as high as where it bounced it from, that's because it lost some energy in the process of bouncing. Well, where did that energy go? Well, one of the things you might not think about is the sound, right? What's producing the sound? That physical force is making the sound. It's pushing out sound waves and disrupting the air. So if you bounce a rubber ball and it makes it like boom, right? That bounce, well, I can't really make the sound with my mouth, but you know, the bounce sound, right? That sound is some of that energy. The sound being made there is one of the reasons it doesn't go as high, right? It probably generates a little bit of heat as it pushes up against the friction of the chair. You might not really feel it, but if you hit something a lot, you might start to feel warm. You can rub your hands together, right? Rubbing my hands, that's making a sound. That's where some of the energy is going. It's also generating heat. That's where some of it's going. And sometimes I'm just physically pushing energy. I'm pushing the air. I'm doing all sorts of things, right? So the ball also had to push through the air. It generated a little bit of heat. It made a sound. It lost energy, in a bunch of ways. And it didn't really lose energy because it's not destroyed, but by losing energy we mean it transferred onto other things. Generally, when we talk about energy loss, that means the energy is transferred onto things that wasn't really our intention, right? Like a car engine. We would love it if a car engine was completely energy efficient. But car engines heat up, right? They can overheat because it's not completely efficient. It loses stuff in heat, right? It makes a sound when you turn it on. It loses stuff in sound. All sorts of things like that. So energy can be transferred from one object to another. That's a lot of what we'll be talking about. In fact, right, we experience energy transfers constantly and we might not know it. Energy can't be created though, and it doesn't vanish, doesn't disappear, even if it seems like the energy is gone, right? If you put in batteries into an old Game Boy and you play it for a while, well, that energy was transferred into light that was emitted from the screen, and it was transferred into sound that was played by the Game Boy. As well as I'm sure other things I just can't think of off the top of my head. Right, physical moving parts. So, the total, I know this is a lot of writing, the total energy of a sample of matter is the sum of its kinetic energy. That is the energy of the motion. Potential energy is the energy of position. A few other types of energy that are important. These are all types of either kinetic or potential energy. Electrical energy. This is the energy associated with the flow of electrical charge. This is a type of potential energy. Thermal energy. This is the random motions of atoms and molecules in matter. And finally, chemical energy, a form of potential energy associated with the position of the particles that compose a chemical system. These are really the three most important types of energy for chemistry. Now, honestly, thermal energy, right, is really just our way of differentiating it from normal kinetic energy, like running around, right? But it's kind of the same thing. Like, it's really not different. It's just kinetic energy on a really small scale. The only reason we differentiate it is because it's so small that we aren't really experiencing that scale. So, pause this if you need to. Just, like, don't worry about every little thing here. Just get the unit down. I'm not going to quiz you on history. I just like giving you bits of information that might help you remember stuff. SI unit for energy is called a joule. It's named after an English scientist who first demonstrated that energy could be converted from one thing to another. He was basically showing, right, well, Isaac Newton showed the law of conservation of energy, but he was showing, right, energy conversion. So a joule is our standard unit that we will be using. Next is a calorie. Now, this is going to be a little weird because we have a calorie and then we have a calorie. When you look at a wrapper of food, you do not see calories. You see calories, right? Check it. You will see in uppercase C, right? Calories. A little c calorie, it sounds a little weird, but the exact amount is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So, we have 1 gram of water raised by 1 degree Celsius for 1 calorie. So think about this. That's a lowercase c calorie. An uppercase c calorie is 1,000 lowercase c calories. That would be, right, you could take a whole liter of water, and with a single calorie from food, you could raise the whole liter by 1 degree Celsius. If it's already in a gaseous form, no. This is really liquid form water. You can't really raise the 1 gram of water by 1,000 degrees because you're just going to start boiling it, and instead the energy is going to go into boiling it. Right? But you get the idea. So, last one is one that you don't need to know for chemistry. I'm just mentioning this for you, for your personal purposes. A kilowatt hour is 1 kilojoule per second times 3,600 seconds that are in an hour. It is the amount of energy. It's basically the amount of energy being used in an hour. This you will someday see on your electrical bill. If you look at appliances, many appliances will give the kilowatt hours. So you can check how many kilowatt hours something will use, how much energy it will use in an hour. Right? So you can estimate the cost of running something for that hour. So this was a while ago. This is probably not true now. I would discount this price of 12 cents. But you know what? We can figure out the price. Average cost of energy, kilowatt hour, United States. 23 cents. Great. It has doubled in the last 8 years. That is kind of sad. Wow, I would thought, all right. Well, now that we have that depressing wake-up call, let me change that. There we go. So again, a big C calorie is 1,000 little calories, and 1 little calorie is actually equal to 4.184 joules. That's the exact amount of water that it takes to heat a gram of water by 1 degree Celsius. Now, this might seem like a number that you wouldn't really need to remember, but you'd be wrong. Remember this number. It will make your life a lot easier. In fact, if you ever want to go into science, you probably need to have this number memorized. That is what we call the calorimetry constant of water. And we don't just use it for converting units, we use it for tons of calculations. You don't need to know the kilowatt hours, but you should know the 1,000 calories, right? If you're in Europe, they would actually just call this a kilocalorie. It would say kcal, which you might see on food wrappers in Europe. So, quick unit conversions. I wanted to remind you guys we did unit conversions a little bit earlier this year, right? I talked about how you've been needing them. We're going to start needing them now. We're going to need them even more going forward. You take your given, the amount that I give you. So I say a candy bar has 225 calories, big C. How many joules does it contain? Well, we'll do 2 conversions. First, we have a relationship between calories, big C, and calories, little c. Then we have 1,000 little c calories per every 1 cal. Then we have 4.184 joules per 1 little calorie. So first, we multiply by 1,000, then we multiply by 4.184. Right? We cross these out just like variables. If you multiply, right, if you divide by that variable, you cross it out, right? We get the new variable of calorie. We divide that, we get the new variable of joules. Obviously, these aren't variables, these are units, but they work the same way. And finally, we end in joules. Always trust the units in these problems. If you are having trouble, stop thinking. Look at the relationships you have. Just say, given these relationships that I know, how can I flip these so that they cancel out diagonally and I'm just left with the one I want? Even if you feel like it doesn't make sense, do it, because the units don't lie. The only time that wouldn't work is if you are using some sort of equation that's only used in specific circumstances, right? Of like, this equation is true in this situation, but not that situation, right? But if you don't know, can't hurt. I don't know why I pulled out that. Actually, let me check our time. We're at 32 minutes. Okay, I'm going to keep going, especially because this is just going to be all class, so I'll probably go for 45. All right. So let's talk a little more about potential energy. I talked about it with the chair, but potential energy, do I have more? Okay. Potential energy is the energy of something's position, right? Or composition. Here's a 10 kilogram weight sitting on top of a building right on the edge. With one little poke, it will fall over. Right. Or here is a little cap being balanced on the tip of my finger. With one little poke, one little wiggle, it will fall over. It has not really a high potential energy, but a high potential energy for what it is. Right now, right, it is unstable. It is getting ready to fall. It has energy with it. When it drops on me, I will feel it because its energy will be imparted on me. A 10 kilogram weight, that's 22 pounds, you will also feel. Just drop that on your foot. You will feel the energy. So, I let it drop. I feel it. I don't know if you heard the sound it made, right? As it hit things, the sound it's making is that other, energy being imparted, as well as the force it gave off onto me and then the floor. Once it's on the floor, it has a low potential energy. It's stable. Right? It's not giving off any energy anymore. Systems with high potential energy like to go to low potential energy. So we're not really going to talk about physical things like that in chemistry. Instead, we're going to talk about chemical energy. Things with a lot of chemical energy tend to be dangerous and unstable and reactive, right? Those are those chemicals we talked about, right? The alkali metals that will explode if they touch water, right? Or the halogen gases that will tear through things that are poisonous, that will react with stuff extremely quickly, right? In order to get an extra electron to fill their octets. One example of this is TNT, trinitrotoluene. They have really high potential energy because the chemical bonds they have are really, really unstable. They're just waiting for anything to set them off, even a physical force, right, that will allow them to go a rapid chemical change. One of the most highly potential energy substances out there. Let's see. I think it's triiodide. No, nitrogen triiodide. Here's just a really slow-mo view of this. It doesn't make that much in the way of sound.
It's always good to start.
So I'm just going to mute this. I don't even know if the sound is coming through. All you have to do is touch this chemical with a feather, and it will explode. Right? That is how little it takes. So a balloon going on it will explode. Right. Let's see if he does a feather. Mosquito landing on it. Yeah. Right. That would be something with a really, really high potential energy. Things that we use as explosives have an extraordinarily high potential energy. And really, the explosion is just the molecules rapidly changing into more stable chemicals. After the explosion, they're usually extremely stable chemicals. Now, the nitrogen triiodide doesn't have anything too stable it can turn into, which is why even though it goes off at the drop of a hat, it's not like the explosion is that big. But something like TNT, well, usually the nitrogens like to break up and form nitrogen bonds, which is one of the least reactive, most stable bonds out there. So almost all explosions have nitrogen because it has a possibility to go from like a really, really unstable thing to a really, really stable thing, right? Whereas the other one, like the nitrogen triiodide, is really unstable, but it can't change to anything too stable, so it's like going like here, right? Whereas the TNT, that's going like down here. It's a much bigger gap. Right, so this line here is bigger. Alright, what else do I have? I'm trying to decide if I want to get into heat today. Where are we at right now? 40 minutes, okay. I'll talk about this last thing, and then I'll end here, and I won't go into heat today, because heat is a whole thing of itself. I just want to talk about exo and endothermic reactions, and even these are kind of related to heat, but not fully. So, exo and endothermic reactions. As far as energy goes, we have two types of reactions, and really these don't have to be just reactions. These can be any type of process. I'll talk about reactions in a moment, and then I'll talk about processes afterwards. An exothermic reaction is one where energy is released. Right? Exo means goes out of, right? Or outside of. So an exoskeleton is a skeleton outside of the body. Exit is a way to leave and go out of something, right? Endo, we don't really use the word endo too much in common vernacular, like commonly, right? But endo means go inside of, or it's like enter, exit, right? Those come from these roots. So you can think of endothermic as energy entering we'll call it the system. So actually, I really want to talk about that real quick. A system is like, well, just whatever you're looking at, right? So I could decide that my body is the system, right? So an endothermic reaction would be something where heat is entering my body through a chemical reaction, where exothermic reaction is heat leaving my body. So the biggest example of an exothermic reaction, fire, right? Something burning. It seems a little weird, right? Because we're like, oh, heat, like energy is exiting, energy is being released. It's not going into it. Yeah, it's not going into it. It's being released, and that's why you feel it, right? It's giving off all that energy. So it's not that it's gaining a ton of energy and that it gets so hot. Instead, it's getting rid of so much energy that you feel all that heat, right? You feel all that energy. Endothermic, right, would be when something gets colder. So think about a cold pack and a hot pack, right? If you have the ones where you like crack them, right, and then it just starts getting colder, it starts getting hotter. That's a chemical reaction. So a hot pack, a hand warmer, for example, right, that would be exothermic. It's getting rid of its heat, and so the heat goes to you. Endothermic, right, is where it's absorbing heat, and so it takes that heat from you. Now, that would be, right, the reaction itself, the reaction happening in the hot pack, the chemical in the hot pack. The process of you getting it is actually a physical process, right? You aren't reacting. The hot pack or the cold pack is reacting. So for you, you can also have an endothermic or exothermic physical change, physical process, right? You shake hands with somebody, they have cold hands, right? You feel their hands as cold, they feel your hands as cold, as warm, right? Warm person gives their energy to the cold person. The warm person is undergoing an exothermic process. Their energy is going away. The cold person is undergoing an endothermic process. Their energy is going in. So when you feel something endothermic happening, you feel cold because your energy is going to it. Right? If you touch a cold chemical reaction, right, that chemical reaction is being powered by absorbing your energy. Your energy is going into making it happen. If you touch a hot chemical reaction, you're taking in the energy being given off by it. All right, I'll leave it there. That kind of is bordering on heat, but it's not quite getting into it, so I'll save that for next time. All right, have a great day, everybody. I apologize if I'm not as animated today. Like I said, nose is very stuffy. I hope I'm not sick, but have an awesome day.